Good morning, everyone. I'm here to present our paper on Beyond Typosquatting, an in-depth look at package confusion. This is a collaborative effort between Worcester Polytechnic Institute, the University of Kansas, and University of Calgary. So firstly, what is package confusion? A presence of a package that can be confused with some other package in language-based ecosystems like PyPy, NPM can be considered as package confusion. Package confusion has some implications in the security of the ecosystem as a whole, as well as the applications that utilize these packages. There have been many articles posted by security media about large-scale package confusion attacks, and here we can see an example of a confusing package, ml-learn-lib, which was uploaded into PyPy. And the original package that it was trying to be confused with was learn-lib and ml-learn. The malicious behavior in this scenario is that it downloads and executes a third-party crypto miner. And interestingly, ml-learn-lib does not directly have the malicious behavior, but it actually has a dependency, which is the one that runs the malicious behavior. Now, when we talk about confusion, people have an intuitive notion of how package confusion occurs. We all get confused, but any research that has happened has usually been limited to typos on lexical text-based changes in package names, and that is how confusion occurs. So our goal was to understand whether package confusion happens beyond typos or lexical confusion, and can we detect it algorithmically. The impact of package confusion, according to our research as well, we found that there are two types of package confusions that can occur. First is intentional confusion, in which a package is intentionally uploaded into the ecosystem with some malicious behavior, which can adversely affect the developer or the application users. And second is unintentional confusion, in which a package name just happens to be confusing with something else. But it still has some security impact because it may degrade the quality of the project in which the confusing package has been used by potentially adding in unmaintained or vulnerable code to the project. So our contribution is that yes, package confusion does occur beyond typosquatting. We consider 13 different categories of confusability. We find potentially confusing packages in the wild and evaluate the effectiveness of the detection rules. And finally, we evaluate the security impact of package confusion. Our research focused on three distinct parts. The first is identifying and collecting past attacks and categorizing it to find the different confusion types. The second is when we talk about package names, it is distinct from normal English because it has different tokens that make sense in the technical language, like ml, learn, or lib, which is not present in the English word. So we had to have some domain-specific tokenization, and then we built prototypes to be able to detect these different confusion categories. And finally, we evaluate by applying the detectors to NPM, and finally evaluate the results that we get. So our first step was collecting past historical data. We did this by utilizing specialized media or articles by threat intelligence companies or different security advisories. And we collected over 1,200 distinct packages that have been uploaded into multiple ecosystems, NPM, PyPy, and Ruby gems, and and then we found over 7 campaigns in which more than 10 packages were uploaded all at once. For our analysis, we mostly utilize NPM because it is the largest of all 3 ecosystems. Our next step was to find what kind of confusion or confusability categories these attacks occur on. So to follow a rigorous process, we performed thematic analysis on the package confusion names. And then after multiple rounds of thematic analysis, we came up with 13 different distinct categories of package confusion. Here we can see on the right side the distribution of the different categories in our attack dataset. The next step was to build detectors for these package names. But we realized that a number of our detectors needed transformation of packages into a sequence of tokens. And usually these tokens were not separated by known delimiters. An example would be that, as I said, ml_learn lib, well, ml_learn and lib are distinct tokens that are in the packages, but ML is something that does not have a valid English connotation, but it does have technical language connotation in the technical language. So we built a delimiter-less tokenization algorithm using NPM package names. And here we can see an example of breaking down the package names into multiple smaller tokens. And only after that, we apply the detection rules. In this case, the detection rule that applies is the prefix-suffix augmentation, as there is the addition of lib in the confuser package. Here is a result of the performance of our detection rules. Our goal was to maximize the chances of identifying confusable packages, even if we miss some attacks. We accounted for the significantly imbalanced samples. We had some with a lot of samples in the same category, some with very few, and we tried to maximize the precision. Finally, let's look into how we evaluated our detection rules. So we had 4 research questions. The first is how many potential instances of package confusion exist in the NPM ecosystem. For this, we apply the detection rules to NPM. We focus on popular and unpopular package pairs, and we use the same popularity threshold that we use in our previous work, TypoGuard, in which we believe that anything that is more used or has more weekly downloads can be considered as popular or the established original package, and anything that is trying to be confusable to this popular package is the one that is most likely to be malicious or adversarial. So this reduced our analysis space to around 1.7 million confuser packages to 24,000 established packages, which drastically reduced it from like 1.7 squared NPM package pairs that we would have to utilize. So here is the result of our matches. We found over 360,000 package pairs which can be detected as confusing, and over 3,000, almost 3,000 of them matched multiple categories. The results that we found were that we have one which is a popular package and one which is an confuser package, and it's a package pair that we got results as. The next step was to find out how confusing these identified matches are. For this, the main victim of package confusion are, of course, developers. So we recruited 64 student developers and asked them to rate how likely they are to misremember or mistype the package pairs. We had a column with the confuser and a column with the original package pairs. The goal of this survey was to determine which rules can return reliable matches. Here is a result. Some of the most interesting results here is that 3 of our categories had more than 10% of the users identifying it as highly confusing. That is more, all 3 of them rated it as more than 5, and then more than 70% of them had marked it as potentially confusing. So these 3 categories could potentially be used as a warning mechanism, whereas 2 of them had less than 25 potentially confusing, less than 25% marking it as potentially confusing. And we believe that it may be either because of the imbalanced samples that we had, or it may be because we had a more generalist detection rule, which could potentially have caused it to be not considered as confusing for users. So finally, our third research question was, what is the security impact of the identified confusing packages? So for this, the goal was to assess the density of the malicious packages among the detected confusing packages. The problem here is that we don't have a ground truth. We couldn't go and analyze each of the packages as whether they were malicious or not. So the solution that we found was to analyze existing vulnerability database as a potential lower bound to see how many of them are malicious. So the result shows that packages flagged by our rules are 3 times more likely to be malicious than the control data set that we used. Here is the distribution of the malicious behavior. We categorize them, the flagged malicious packages as per Duan et al. And then we also added 3 new categories, crypto theft and downloader and confusion. In many cases, we could not verify the malicious behavior because of the removal of the packages from the ecosystem. So finally, to conclude, we see that package confusion is a credible threat, and hopefully our categorization will help to specify how attacks may occur. And our categories provide a new dimension of package confusion beyond just typosquatting. And while some of our detection rules may benefit from refinement, some of them could be used as a warning mechanism as it is. Thank you so much. Please email me if you have any questions, and I'm also happy to take any questions right now.